Hello everyone. Today we will start with the fifth lecture, and we provided a review of first order transients, and today we want to move on to second order transients. But before we do that, I wanted to discuss a methodical way of analyzing any first order circuit with one storage element. So if you have a certain circuit and you have only one energy storage element only, so this is the circuit. You have either an inductor or a capacitor with the rest of the circuit, right? So there's an orderly, methodical way of doing that analysis that applies to any variable within the circuit. So the example we went through for both an inductor and a capacitor were examples where we solved for the state, was called the state variable, which is the variable that carries energy. For a capacitor, it's the voltage of the capacitor, and for an inductor, it's the current of the inductor. Those are called state variables because those are the variables that carry the energy in the system. Because the capacitor carries its energy in its voltage. The energy of a capacitor is half CV squared. The inductor carries its energy in its current. Right, so the energy is half Li squared. We're gonna review a bit energy and power. I got a request to do that during hours today, office hours today. All right, but we will do that. But first, let me go through this methodical method. So this methodical method has 6 steps, as described in the textbook. Right? So, and we're gonna go through an example that demonstrates those different steps. So step 1 is we assume the solution is gonna have this form. We know the solution is gonna have this form, right? Because why do we know it's going to have it? Because it's a first order system, right? Because it's a first order system, the solution, regardless what variable we're solving for, the solution is going to have this form. Now the particulars of the solution will be what give us K1 and K2. K1 and K2 will depend on what variable in the circuit you're solving. They will vary between different variables, right? But the solution itself will have this general form. Right? And we said that typically what we do is we assume that there's a transition in the circuit. Something triggers the transient. Let's say some switch gets thrown or whatever, right? So before that event occurs at t, typically we assume it occurs at t equals 0. Before that event occurs at t equals 0, that changes the circuit, and the circuit goes through the transient until it reaches steady state again. The circuit beforehand was in steady state. So there is a steady state before the transient, and there's a steady state after the transient, right? And the transient is in between. So we want to the assumption is that the circuit already, in this analysis, the circuit already reached steady state before the transient. That doesn't have to be. We could have had multiple transients. We could have had an older transient, and then the new transient happened before the old transient was finished. Right? We don't want to go that far. We just want to assume at this point that any previous transients in the past are long gone and finished. And by the time this new transient occurs, this transient of interest at time equals 0, we want to assume that at that time the circuit is in steady state already, previous steady state. Right? So we assume that the original circuit reached steady state. Why is that important? That allows us to calculate any capacitor in the circuit. We can use regular circuit analysis techniques to calculate the capacitance voltage and the inductive current, right? And we know from circuits 1 that we treat a capacitor at steady state as an open circuit. At steady state, after things are settled, the capacitor in the circuit is treated as an open circuit, because at steady state, we said C dV by dt. At steady state, dV by dt is 0. V doesn't change anymore, so I is 0. Right? So the capacitor is treated as an open circuit in steady state. The inductor is treated as a short circuit in steady state. Why? Because V equals L di over dt. At steady state, di by dt is 0, so V across the inductor has to be 0. What has a 0 voltage across it? A short circuit, right? So and instead of the inductor, you substitute a short circuit. Instead of the capacitor, you substitute an open circuit, and you solve for the voltage of the capacitor and the current of the inductor just before the transient. So you have those values, you keep them, track of them, right? The other major property of the capacitor and the inductor is that the capacitor voltage has to be continuous, while the inductor current has to be continuous. The capacitor voltage cannot vary instantaneously, and the inductor current cannot vary instantaneously. Well, that's evident from their equations, right? From their VI equations, because if the capacitor voltage varies instantaneously, we will get infinite current. If the inductor current varies instantaneously, you will get infinite voltage, right? So we use that property to get IL0 plus and VC0 plus, which will be the same as the voltage and the current just before the transient event. Right? So because of the continuity of the capacitor voltage and the inductor current, that allows us to find their values after the transient, and we use those values to find the state variable or the variable we're solving for just after the transient. Right? And then we have that initial condition, and then step 4 involves finding the steady state solution for the variable. The steady state solution, again, is easy. Steady state solution is x at infinity, and again we go back to the circuit and we apply the rule of thumb, the rule that capacitors are open circuits and inductors are short circuits. Okay. Step 5 involves finding tau, right? And it involves using the formulas that we found. We found that tau equals RC for an RC circuit, tau equals L over R for an inductive circuit with an inductor. And again, let's say we're not sure about the L over R. How can we check? Well, we know that VL equals L di by dt. So L has units of volt second over amp. Right, so I want to check that this gives me seconds. So I have volt second over amps. What's the inverse of R? Inverse R is volt over amps. So the inverse of R is amp over volt, right? Right, so the inverse of R is amp over volt, because R has units of volt over amp. Okay, this cancels properly and we get seconds. So if you're ever unsure about the formula, you're not sure, hey, is this R over L or L over R, you can just check the units. Right? The idea is that we could have a complicated circuit. We could have some kind of circuit that has many elements, many resistive elements, let's say, and many voltage sources and current sources and whatever, right? It could have dependent sources. Right? But what we could do is we could always reduce the circuit connected to the energy storage element, either resistor or capacitor, into a Thevenin equivalent, and then take that Thevenin impedance, R Thevenin, right? That's what gives you the time constant. Couple it with C and get the time constant, which will be R Thevenin C, and tau for an inductive circuit is going to be L over R Thevenin. The time constant will be the same in a first order circuit for any variable in the circuit. Whatever variable you're measuring, let's say you're measuring the voltage across this resistor or the current across this resistor. whatever variable you're measuring in the circuit, the time constant will be the same everywhere. That's a big property of first order circuits. You won't find different time constants, right? For higher order circuits, yeah, you will have different time constants dependent on which energy storage element is connected to what part of the circuit. But that's for higher order, second order or higher. For first order circuits, the time constant will be the same everywhere. So step 6 involves combining everything together. From the initial condition after the event, we can plug in t equals 0 and we have the equation for k1 plus k2. And then k1 is going to be the steady state of x, right? So we have two equations and then we can two unknowns, and then that means we can solve k1 and k2. The solution will be evidently k1 equals x infinity, and k2 is going to be x0 minus x1, which is x infinity. We plug in and we get this form, the solution. And that's it. Those are the 6 steps. So I'm going to give you an example of those 6 steps. Not a very complicated circuit, an example from the textbook, but a good demonstration of applying those 6 steps for a variable other than a state variable, meaning other than an inductor current or a capacitor voltage, right? So let's do the example, right? So let's say I have this circuit, 36 volts, 2 kilo ohms, and I have a 100 microfarad capacitor. Then I have 6 kilo ohms, and then I have my switch here that shuts off at t equals 0. And then I have a 4 kilo ohm resistance, and then another supply, two supplies, 12 volts. Okay, and as we said, we are going to stick, in the beginning of this course, we're going to stick with DC sources. Those are the transients that we will solve for. So those are transient events with DC sources in the circuit. We can handle any general source, that's solvable too, but that requires us to finish the course, to get to the point of the Laplace transform. Once we understand the Laplace transform and how it applies to circuits, we can solve for any general source. Okay, so yeah, let's apply the steps. So, the variable we're solving for, we said we want to solve for this methodical approach is useful when we are solving for some variable other than a state variable. So let's solve for IT, this current. This is not a state variable. This is not a capacitor or an inductor. So applying step 1. Well, step 1 says, hey, you're sure whatever solution is for IT, it surely has the form I of t equals k1 plus k2 e minus t over tau, right? Step 2. What's the energy storage element? The capacitor, right? So we have VC, right? So we want to find VC 0 minus, meaning the voltage of the capacitor just before the transient. We want to find that because we know that the voltage of the capacitor is continuous, cannot vary instantly. So the voltage of the capacitor just before the transient is going to be exactly the same as the voltage of the capacitor just after the transient. Right? So the assumption is that just before the transient, the circuit has already reached steady state or is already at steady state. There are no older transients that are still happening. Any older transient has already subsided by that point. Okay, so the thing that we need to do is that the capacitor is going to be an open circuit. So I'm going to redraw the circuit. So I have 2 kilo ohm. The capacitor is an open circuit. VC 0 minus, plus minus, and then 6 kilo ohm, and then I 0 minus, and then 4 kilo ohm, and then here plus 12, right? So I'm interested in seeing what the current is before the transient, and the current also will help me finding the voltage. I mean, there are many techniques of solving this. You already know you can use voltage divider, you can use KCL, KVL, whatever regular circuit techniques we're going to use to solve for this. So this should be like something you've mastered at this point, but we're going to go through it. So what's I0 minus? I0 minus is just the voltage across those resistors divided by the resistance, right? The voltage is 36 minus 12 volt divided by 12 kilo ohms. Right, so what's 36 minus 12? 36 minus 10 is 26. 26 minus 2 is 24 over 12 milliampere. So that's 2 milliamperes. That's what I0 minus is, 2 milliamperes. So what does VC0 minus, what does that make VC0 minus? Well, one way of calculating it is by subtracting from 36 the voltage drop across this resistor, right? So this current is passing through this resistor, 2K, and there's a voltage drop associated with it. So what's the voltage drop? It's going to be 36 minus 2 kilo ohm times 2 milliamperes. Right, so it's going to be 36 minus 4, the K goes with the milli, we end up with volts, yeah. 36 minus 4 volts. So that's going to be 32 volts. So that's VC0 minus 32 volts. This value is going to carry over to after the transient. This is going to be equal to VC0 plus. Okay, so now step 3. Using this capacitor voltage that carries over just after the transient, we want to now solve our circuit variable after the transient. What the transient does is that it changes the topology of the circuit. It changes the circuit itself. What does the transient do? It turns on the switch, closes the switch. This changes the circuit, right? Instead of the original circuit, now we have this circuit. So we have 36 volts, 2 kilo ohms. I'm not going to draw the capacitor now. 6 kilo ohms. And then this becomes a short. And then this is 4 kilo ohms, 12 volts. It's like we separated the circuit into 2 independent circuits. And now we want to solve for I just after the transient. And we said the trick here is that the capacitor voltage is continuous. That means just after the transient, the capacitor voltage will have this value, and we can plug it in as a voltage source. So this is going to be VC0 plus. Right? It's just a fixed voltage source of 32 volts. Okay, clearly this 32 volts applies directly through this short on the 6 kilo ohm resistor. So that tells me that IO0 plus equals 32 over 6 kilo ohms. That equals what? That equals 16 over 3 milliamps, which equals 5.33 milliamperes. Okay, that's step 3. Step 4, we want to find now the steady state value of the circuit variable we're solving for. So we want to find I at infinity, or I of t as t approaches infinity, to write it in another way. Okay. Again, at steady state, the capacitor is a open circuit. That's what the capacitor is. This is VC at infinity. resistor, 6 kilo ohm, another resistor here, 2 kilo ohm. This is still shorted out. This is 4 kilo ohms, and this is 12 volts. Okay, and what's I at infinity? This is an open circuit, right? I at infinity. Now this part is shorted out due to this short. So I at infinity will be just 36 applied to those two resistors, 6 and 2. So I at infinity will be 36 over 6 plus 2, 8 kilo ohms. Right? So that's going to be yeah, volts over kilo ohms. So that's going to be, what's 36 over 8? That's going to be 18 over 4 milliamps, 9 over 2 milliamps. That's going to be equal to 4.5 milliamps. Okay. And then step 5 is finding the time constant. Under what conditions finding the time constant after the event happens, after the switch is closed? That's the circuit where the transient is happening. So what is the time constant for this circuit? Well, one thing we can do is we can draw the relevant circuit. This is C 100 microfarads. We have a resistor here, which is 6 kilo ohms. It's shorted on this side. I can ignore the rest of the circuit because this is a short and essentially bypasses the rest of the circuit. And then 2 kilo ohms, and then 36 volts. I want to find the Thevenin equivalent of this. And you know how to find the Thevenin equivalent, right? You first find the open circuit voltage. What's the open circuit voltage in this case? Well, we don't need the open circuit voltage. I don't want to find the exact. This is the Thevenin equivalent, V Thevenin, R Thevenin. I really don't need to calculate V Thevenin. All I need to do is calculate R Thevenin because the time constant has no use for V Thevenin. What is, and this is C, of course. What is R Thevenin? R Thevenin is, I just look from those two nodes, I try to find what the equivalent resistance is, right? The voltage source turns into a short, right? So I end up with just 6 being parallel with 2. So R Thevenin is 6 kilo ohms parallel with 2 kilo ohms. If you don't remember Norton's or Thevenin's theorems from circuits 1, please review them. It's a very basic technique of circuit theory, right? We don't need to calculate V Thevenin, but if we wanted to, V Thevenin is just going to be the voltage that appears here, assuming this is open, of course. There's no load, right? So that will be just simply a voltage divider. That will be 36 times 6 kilo ohms over the sum, which is 8 kilo ohms. If you do the math, this turns out to be 27 volts. This won't be used, but R Thevenin is going to be the paralleling of 6 kilo ohms and 2 kilo ohms. We know how to find that. We take their product over their sum. That's one way of doing it. So this is kilo ohms over squared over kilo ohms. Right? So we end up with kilo ohms, and that will be 12 over 8, 6 over 4, 3 over 2. So R Thevenin is going to be equal to 1.5 kilo ohms. Right? Now we have all the ingredients. Well, before we do that, let's calculate the time constant. The time constant is going to just be RC. So that's going to be 1.5 kilo ohms times 100 microfarads. Right, so kilo times micro is going to be milli. It's going to be millisecond. 1.5 times 100 is going to be 150 milliseconds, or 0.15 seconds. That's the time constant. Okay. The final step is putting it all together. right? We know I0 plus is going to be K1 plus K2. We know I infinity is going to be K1. Right, so that gives me the final form of IT. Instead of K1, I put I infinity. Plus, instead of K2, I put I0 plus minus K1, which is I infinity. E minus T over tau. And writing it all down, we get I of T equals 4.5, that's I infinity, plus the difference between 5.33. This is 5.33 and 4.5. This turns out to be 0.83 E minus 1 over 0.15. 1 over tau is going to be 6.66 T. Milliamperes. So this is the solution using this methodical 6-step method. You're free to use it, or you're free to freehand the solution. I mean, I'm fine with either, but just for completion, I just wanted to go through this method. It's an interesting method, and it's a good way of thinking in a methodical manner. How would you analyze any general variable? How will you solve for any general variable in a circuit other than the capacitor voltage or the inductor current? Right. We said the interesting thing, by the way, what was I0 minus? This is an interesting point. I0 minus, we solved for it earlier. So I0 minus was 2 milliamps, right? So clearly, unlike the capacitor voltage, this variable is not continuous, right? It doesn't have to be because it's not an inductor current. The only variables that need to be continuous are the inductor current and the capacitor voltage. Any other variables in the circuit can show discontinuity. Right? So I0 is minus is 2 milliamps. So if you plot the response versus time, where the event, the transient happens at t equals 0, the current used to be 2 milliamps. Then at t equals 0, e to the power 0 is 1. Right, I have 4.5 plus 0.83, so the current jumps to 4.5 plus 0.83. I don't want to do it, too lazy to do the sum, right? And then it starts at t equal infinity, it will go to 4.5 milliamps. So there is this jump initially in the current. The current suddenly jumps to this larger value, then it dwindles down to 4.5 milliamps. At t equal infinity, this term becomes 0, this term. Okay. So there is this discontinuity evident in the response. And you would see that in any variable other than a capacitor voltage or an inductor current. Okay, second order transients. So those are the kinds of transients that arise when we have two energy storage elements in a circuit, two differing energy storage elements, or I guess energy storage elements that are disconnected. So if I have something like this, for example, this is still not a second order system because I can always sum those two caps and find the equivalent capacitor. It's equivalent to one capacitor in the circuit. But if I have something like this, let's say resistor, and then a cap, so those two caps are separate, there's no way to combine them together to find an equivalent capacitance, then that would be a second order, right? And then another example is a circuit where we have somehow two inductors, right? But the most general kind of second order circuit is a circuit that has both an inductor and a capacitor, right? This gives us, if you have a circuit that has both of those elements, that will give us the most general types of responses, right? So the canonical circuits, the canonical second order circuits are as follows. They could either come in a series variety or a parallel variety. So we could have a resistive element, resistor, an inductor, and a capacitor all in parallel. And in this case, the state variable is going to be the voltage across those parallel elements. And then the forcing function is a current. It has to be a current because if we make it a voltage, I mean, it will force the voltage to be whatever the voltage supply is, regardless of what those elements are doing, right? So we make it a current so that we solve for the voltage. And then there's the series connection where we solve for the current, and we have a resistor, a capacitor, and an inductor. And then the source is going to be a voltage source. It cannot be a current source because the current source is just going to force the current to be whatever the source dictates. There's nothing to solve there, right? So both of those are canonical representations of a second order circuit, and we can get the differential equations representing any one of those by using regular KCL and KVL. For example, for the parallel connected components, we can use, in this case, KCL, right? If we use KCL, we get, so all three currents need to be equal, right? So we end up with V over R plus, what's the current through the inductor? So the inductor has this property, right? So it's VL equals L di by dt, and the inverse, we have to invert differentiation, so IL is just going to be 1 over L, the integral of VL x dx. X is a dummy variable, and we're integrating from the starting time of the transient to the end time of the transient, right? Plus some initial condition. So the inductor current could have some initial condition. It doesn't have to start at 0. So you can just plug that in. So we have 1 over L integral from some initial time to time t of Vx. X is a dummy variable, dummy integration variable, right? Plus the initial condition, plus the capacitor current, which is simply C dV by dt, right? This equals Is of t. And then the other equation, using the series circuit, we apply KVL. So applying KVL, we get R I of t plus what's the voltage across a capacitor? Well, it's the integration of the current, right? So it's going to be 1 over C integral from t0 to t, right? So that's a relationship for a capacitor. We differentiate the voltage to get the current, and we integrate the current to get the voltage, right? Plus the initial condition for the cap. The cap could have an initial voltage on it, plus the voltage across the inductor, which is simply L di by dt equals Vs of t. Okay, so those two kind of equations are kind of like hard to deal with because they are they have both integration and differentiation. We'd rather than working with equations that have integration in them, we would rather work with equations that are purely differential equations. The easiest way to turn this into a purely differential equation, both of them, is to just differentiate again. Right? So if I differentiate again, I get, let's see, differentiate this term. I get C d squared V over dt squared. I differentiate this term, I get 0, it's a constant, right? I differentiate this term, What happens if I differentiate an integral? I get what's the opposite or the inverse of integration? Differentiation. So if I differentiate an integral, I get the original variable or inside the integration. So I end up with plus 1 over L dv by dt. Right? Is this correct? I made a mistake somewhere here, right? Oh no, this is fine, right? So 1 over L dv by dt, and then finally v over r. So oh, I know what mistake. Oh, there's no dv by dt. So I'm differentiating an integral. I get the opposite inverse of that, which is the variable inside the integral. So I just get v over L. Okay, that was my mistake. And then this I'm differentiating. I get 1 over r dv by dt. This equals dis by dt. This is the first equation. For the series case, again, I differentiate again. Let me start with this term. I end up with L d square I dt squared. This is 0. This term gives me plus r di by dt, and this term is the inverse of the integration, which is just plus I over c equals dvs by dt. Okay, so both those circuits give me a second order equation, and the response, the transient response of those circuits is going to be dependent on what kind of solution second order equations have. Right, so this is something you study in depth in differential equations. That's a topic of that's a study area, but here we will not study this in general. We will just concern ourselves with solving the second order equation. How can we perhaps if you know this already, this will be a kind of a review. If you don't know it, we will go through it. So to find the response, we need to be able, in general, we need to be able to solve the second order. It all hinges on being able to solve the second order differential equation, which looks like this in general: d square x over dx plus some constant dx over dt plus some other constant x equals f of t, some forcing function. And we will limit ourselves at this point to forcing functions that are just constants, a voltage source or a current source, so on and so forth. So as the same facts apply for any differential equation or for any linear ODE, the solution is going to be a particular solution plus a natural response, natural solution or a homogeneous solution of the homogeneous equation, right? And the particular solution will be something that follows the forcing function. So the particular solution in general would be some let's say constant. Say it's some constant, right? It will be some constant, right? It will be some function that's a constant, meaning that when I differentiate it twice or once, it will be 0. What should it be according to this equation? Well, a2 xp of t equals a, so that constant should be a over a2. So the general solution will be a over a2 plus the solution of the homogeneous equation, the natural response. Right? So we will not concern ourselves with this at this point. This is just a constant. We can always tag along, add to the solution. Let's concentrate on the homogeneous equation, because all the richness of the solution occurs here in solving the homogeneous equation. The homogeneous equation is as follows. D square x over dt squared plus a1 dx over dt plus a2 x of t equals 0. Okay, so this is the part that is mathematically rich, that gives us all the second order phenomena, right? While the particular response just follows the input, which is a constant. From insight gained by this solution, people went back and said, hey, we don't, it will be insightful if we change those constants. You know, those are just constants. We can change them to anything that we want. So it will be insightful to arbitrarily, I mean, if its usefulness will be apparent later, but instead of having two just constants, just define the constants this way. So you define a 2 zeta omega naught and omega naught squared. Again, this has no meaning at this point. Those are just two constants. I can define them anyway. I can make this constant a plus b over c if I want, right? This is a matter of choice. But it's a very useful choice for the constants to have this form. This will have physical meaning as far as the solution is concerned. Okay, we haven't changed the thing. Okay, so we want to solve this equation, and the method, the general method, we can here we cannot use we cannot do integration easily, right? But the easiest method we can use is getting the characteristic equation. Here's where the polynomial shows up and complex numbers show up. So we need to get the characteristic equation to solve this differential equation. And the assumption here is that, hey, assume the solution of this equation has this form, E lambda t. That's an assumption, right? So we plug this assumed solution into the differential equation. The nice thing we said about E lambda t is differentiated once, you get E lambda t times lambda. Differentiated twice, you get another lambda, you get lambda squared E lambda t. It has this nice property where each act of differentiation gives me an extra lambda here that multiplies the E. So plug that into the differential equation. I end up with lambda squared E lambda t plus 2 zeta omega naught. Differentiating once is lambda E lambda t plus omega naught squared E lambda t equals 0. I can take the E lambda t out. I end up with lambda squared plus 2 zeta omega naught lambda plus omega naught squared times E lambda t equals 0. Here's the interesting part. For this term to be a solution at all, this equation must equal 0 for all t. Right? Differential equation is not true only for a certain time, it's true for all time, right? So this, for the differential equation to be true, for this to truly be a solution, this thing must equal 0 for all t. And this thing cannot equal 0 for all t unless lambda is chosen such that this term is equal to 0. Right? So the lambda in the E lambda t that is the solution is only the lambda that's the solution for the characteristic equation, which is lambda squared plus 2 zeta omega lambda plus omega squared equals 0. Solve the characteristic equation and you solve the differential equation, right? And then the solution of the characteristic equation gives you lambda and E lambda, let's say lambda 1. Let's say lambda 1 is the solution of this differential characteristic equation. E lambda 1t will be a solution of the differential equation because it obeys the differential equation. Okay. And here it's clear that we can get from E lambda t, we can get two solutions because this is a second order polynomial. Therefore, it has two solutions. This is the fundamental theorem of algebra. An nth order polynomial will have n solutions. Now, those solutions don't all have to be real. They could be complex, and here's where complex numbers come in, right? but it will have n solutions, and the complex solutions will have physical meaning, will have actual, they will represent actual solutions to the differential equations that arise in real life. So here is a situation where the complex numbers are not really imaginary, so to speak. They have real life consequences in the sense that a complex solution to the characteristic equation entails a certain kind of response for a second order system. Okay, so all we have to do is solve this. We can use the what do you call it, the quadratic formula. I don't like to use this. I just like to complete the squares, right? So I can take this lambda squared plus 2 zeta omega naught lambda. I can add to it omega naught squared zeta squared, and then subtract omega naught squared zeta squared. I didn't change the thing, right? Plus omega naught squared equals 0. Right? So I've completed the square. This term here is a square, so this is just lambda plus omega naught zeta squared. This is what this is, right? Lambda squared omega squared zeta squared, and then 2 omega naught zeta lambda. Right? I've just completed the square, and then I end up here with plus omega naught. Take the omega naught out, I end up with 1 minus zeta squared equals. Right? Take this to the other side, I end up with lambda plus omega naught zeta squared equals, this will become minus, let me take the minus inside the bracket, so I end up with zeta squared minus 1 times omega naught squared, and then solutions are simple to find, right? You just take the square root on both sides, and with being mindful that there is a positive solution and a negative solution. When you take the square root of 4, there's a positive solution, negative solution. Both are solutions to this equation, right? So the square root is positive square root is a solution, and the negative square root is a solution, because when you square the negative you get positive, right? So you end up with first after I take the square root, I end up with zeta omega naught, which I can take to the other side, so I end up with minus zeta omega naught, and then the positive square root, which is omega naught zeta squared minus 1, and then the other solution is going to be the negative square root. Same real part, same this part, not real part, minus the negative square root, which is, right? Because both the negative square root and the positive square root, when you square them, you get this value, right? It doesn't matter. Right? Those are called natural frequencies of the system, and they're called frequencies because it will turn out that under some conditions, those represents oscillation happening in the system. Right? Nomenclature. So this is called the omega naught is called the undamped natural frequency. And this is called the damping ratio or damping coefficient. Because it will turn out that this term zeta represents how damp the system is, how far away from being oscillatory the system is. So this is omega naught is a function of how oscillatory the system is. Omega naught tends to indicate or give you at what frequency does the second order system tend to oscillate, while zeta tends to give you a measure of how damp the system is. How fast if there is an oscillation in the system, how fast it dampens down, right? Okay, so those are the two natural frequencies, and this gives me the complete solution. The natural response is going to be, or the response to the homogeneous equation is going to be just k1 e lambda 1t plus k2 e lambda 2t, where lambda 1 and lambda 2 are those two terms. Right? That's it. And because it's a second order equation, notice there are two constants. There are two solutions. There are two constants. Those two constants need 2 initial conditions instead of 1. So now we need 2 initial conditions to find to pin down the actual response for a certain system. So those initial conditions could be the value at some initial time and the derivative of dx by dt at some initial time. Let's say t equals 0. So we need both the initial condition and the derivative, both the x at 0 and the derivative of x at 0 to find the pin down the solution. We could also pin down the solution by having 2 boundary conditions, meaning if I know x at a and x at b, I could also pin down k1 and k2. The point is that if I do x0, that's going to give me k1 plus k2. If I do dx by dt, what's dx by dt? That's going to be k1 lambda 1 e lambda 1t plus k2 lambda 2 e lambda 2t. I'm just doing differentiation of the exponential. And then take this at t equals 0, which means e to the power 0 is 1. So I end up with this second equation. So I have equation 1, equation 2, 2 unknowns, 2 equations, and I know the natural frequencies. I can solve for k1 and k2. Right? So 2 equations, 2 unknowns allow me to specify the unknowns precisely, k1 and k2. Okay. Something is interesting here in the natural frequencies. Notice there's a square root and there's a damping ratio. The damping ratio depends on the characteristic equation, which again depends on the differential equation, right? But notice this value could be anything, right? Eta, zeta. What happens? This is under square root minus 1. So there's a possibility that this thing under some conditions will have a positive number under square root. Under some conditions, this will give me a negative number under the square root. So that's interesting. What happens when I take the square root of a negative number? I get a complex number. So that's how complex numbers seep into the general solution for a second order system. So the presentation is as follows. Zeta, the damping ratio, determines the type of response. And there are 3 conditions. If zeta is larger than 1, this is called an overdamped response. It doesn't show any oscillatory behavior, right? And when zeta is larger than 1, all is good under the square root, it's all positive. Now when zeta is less than 1, we get an underdamped response, meaning we start to see oscillatory phenomena and the frequencies become complex. So zeta is less than 1. So this is less than 1 minus 1 gives me a negative number. We end up with a complex natural frequency. And then there's zeta equals 1, right smack in the middle, where this whole term becomes 0, right? And this is what's called critically damped system. Okay? And each one of those will give us a different form of the response. Let's start with the overdamped. What happens if we are overdamped? So the natural frequencies are as follows. Right? So there is not problem. We have 2 positive numbers, right? And then the general solution is simple. The general solution, I'll just plug it in. The general solution will be a regular exponential solution, but now there will be 2 of them, right? So let me write actually the general solution. The general solution will be let me just do the natural response. Forget about the forced response for now. So it's going to be K1 E. Let me take the minus out. Zeta omega naught minus omega naught zeta squared minus 1. Plus K2 E minus zeta omega naught plus omega naught zeta squared minus 1. So the response is a combination of two exponential functions. So you have two exponential decay functions, you add them together, and that gives you the total natural response, right? Their average is this value, and then this is decaying slightly slower than the other one by omega naught zeta squared minus 1 square root, and this is decaying slightly faster than the first one. And there's an average decay between them, but there are two of them that you have to sum. Okay? That's if it was a first order system, you would have just one exponential decay curve. You won't have two of them. Right? So this is typical of such underdamped systems. You would see sometimes a response like this, where you have for some region some exponential rise, and then for another region, suddenly the exponential rise will be altered. It will be different. Right? So you the waveform will look funny. It will not look like a single exponential. It will look different under different regions. It will look like two different exponentials. Right? You'll learn how to recognize it eventually. Right? Sometimes it's hard to recognize because sometimes exponentials are close to each other, and other times that the difference between those two rates are larger. We can represent it as solutions on the complex plane. So this is the z plane. Right? So when zeta equals larger than 1, the solutions are always going to be on the real line. So you would have something like this, two solutions here, let's say. Right? They could be farther apart or closer to each other. The x represents the solution of the characteristic equation. Okay, one more, yeah. So this is the case where the solutions are real. Okay, what about underdamped condition? The underdamped condition is when zeta is less than 1. When zeta is less than 1, let me rewrite the characteristic equations now. Okay, what happens when zeta is less than 1? This becomes complex. Right? So let's write it in a way where we factor in the complex number. So this becomes less than 1. Right? So this is minus 1. So let's take the minus 1 out and take square root minus 1 as j. So I end up with this form of the natural frequencies, minus zeta omega naught. I took the square root minus 1 out as j, plus j omega. Because I took the minus 1 out, I flip the 1 and the zeta squared. I end up with 1 minus zeta squared. This again becomes positive, right? And then lambda 2 equals minus zeta omega minus j omega naught 1 minus zeta squared. Typically, you will see omega naught 1 minus omega squared designated as omega d. Omega naught, this is what's called the damping frequency, right? And then sigma, a variable sigma, just lumps omega with zeta. Okay, so those are two complex numbers with values minus sigma, the real part of the natural frequency, plus j, imaginary part, which is just omega d, or minus sigma minus j omega d. Okay, so the homogeneous response, the natural response, is just going to simply be the same, right? It's not going to change. But now we will have an e to the power j, right? I would have an e minus this, and then the j would be positive or negative. I can take e to the power minus sigma omega naught out because it's common. And then inside I will have k1 ej omega naught 1 minus sigma squared t plus k2 e minus j omega naught 1 minus sigma squared t. Okay, so this is the general solution. It's a complex solution, right? We don't like to deal with complex solutions because, I mean, a complex solution to a differential equation is valid, right? Because we could have complex functions as solutions, but we want to limit ourselves to real solutions because real solutions are are what we see in real life. We don't see complex, also, although the solution exhibits complex natural frequencies, the response itself, the voltage and the current is going to be real, right? So what we can do is just we can take the real part of the solution and ignore the complex part. Whenever you see a to the power j something t and then a to the minus j, that's very suggestive of trigonometric functions. Why? Because you know the relationship ej x equals cosine x plus j sine x. What about e minus jx? That's cosine minus x, but cosine is even, so I end up with cosine x minus j sine x, because sine minus x gives me minus sine x. Sine is odd, right? Sum those two up and I end up with cosine x equals ejx plus e minus jx over 2. In a similar manner, I could find that sine of x, exactly the same manipulation, equals 1 over 2j ej of x minus e minus j of x. Right? So whenever you find like a sum of two exponential functions, complex exponentials, one with plus j and one with minus j, that's an indication of summing of two trigonometric functions. Right? So the real part of this, the projection of this on the real axis, has to be a summing of sinusoidal functions. So the real form of the complete solutions, we can write it as follows. We can write it as E minus sigma omega naught t, and we're just concerned with the real part. This kind of function will have a projection on the real axis. It's going to be a bunch of sines and cosines. It will have a projection on the imaginary axis. It will be a bunch of sines and cosines. We're only going to take the real part because that's still a valid solution, right? If you have a solution that's complex, you can take the real part separately and that's still a valid solution. And the imaginary part is still a valid solution because linear equations or ordinary differential equations are linear, meaning if you take two solutions and you sum them, you get a solution. Okay, so yeah, so this turns into some. We can write it as, instead of k1, I write a1, and then I'll write the solutions as the real counterpart of the solution, which is just cosine omega naught 1 minus zeta squared t plus a2 sine omega naught 1 minus zeta squared t. And this is the general natural response for the case when zeta is the damping factor is less than 1, meaning the system is underdamped. Okay, I think we're over time, but we will discuss the third condition, the critically damped condition, in the next lecture. Thank you, guys.